So the system that I will be telling you about, an ion trap-based quantum computer that has been built up as at UMD in collaboration with participants Jung-San Kim's group and Ken Brown's group at Duke University, as well as several industrial partners, including AOSense, Cold Quanta, Harris Corporation, and Coherent, a laser company, under the sponsorship of IARPA, which is the intelligence community's, if you will, version of DARPA, with the goal of implementing a encoded logical quantum bit, which within the scope of the full program includes both encoding quantum information into a larger quantum single qubit into a larger quantum system that can correct errors and demonstrating the correction of these errors. In order to achieve that, we have built a single ion trap-based quantum computer, which we call it EURICA, and it's this basically this black box in the sub-basement of the PSC building. Now, in showing the black box, I want to emphasize we're not being very secretive about this. And I can just go ahead and open the box and show you what's inside. And you see that inside it looks a fair bit like your physics experiment, except in a smaller footprint. And that is an important point because all the parts that address the qubits themselves coherently, so everything that performs coherent operations on our qubits, fits inside of this box. And this gives much better environmental stability and has a bit of a side effect, if you will, that once you close the box, even if you wanted to, if you would need to open the box in order to adjust something inside, which would disrupt things. So we had several years of opportunity to develop remote operation to move the actuators inside of the box. And now with COVID, we're great beneficiaries of this, where we can sit at home and do the same thing.
When was the box last opened? Does it sit there for months without being opened?
It was last opened about a week ago, and the main reason why we open it is to service the burns on optics that occur due to UV light. We use high-power UV lasers, and these cause issues on optics. I like to make the analogy to the atmosphere of Titan, Saturn's moon. There's a lot of hydrocarbons on Titan, and even with the relatively weak sunlight there, the sunlight cracks carbon-carbon bonds on hydrocarbons and makes free radicals out of hydrocarbons that can then reform into longer chain hydrocarbons. So from volatile hydrocarbons, you end up with deposits of tarry carbonaceous substances that look like burns on your, in our case, on our optics, because the UV in our case comes from the lasers. And this is the laser.
That purple, those purple streaks that we see in the to the left in the, on the supporting beams, are those ultraviolet? Are those reflections of ultraviolet light?
I think it's actually the flash in this case, judging by the location. The UV would have been coming out in other points, but it would show up similar colored, yes, as blue on the camera. Our wavelength is 355, but I can say that our work, which addresses ytterbium-171 ions, which store quantum information as qubits inside of their hyperfine states. That is analogous to the states that are used for in the cesium atomic clocks with a different atom, with cesium, to set the clock standard, which is the current definition of the second. So the analogous physics in ytterbium-171 ions is used as our qubits. And we trap, each ion serves as one qubit with two states, and we trap up to about 30 ytterbium-171 ions on a microfabricated trap. For scale, the size of this trap carrier, this big square that you see here, is similar to the size of your CPU package on your computer. So this is about 1 centimeter on the side for this central region. And if you see this tiny little black slot, which is 90 microns wide, on top, the ions are floating, suspended by radio frequency electric fields, 70 microns above the surface of this slot. And they're quite strongly held.
And those images, those purple dots we see, is that a real photograph of ion fluorescence?
Correct. This is the real photograph of ion fluorescence taken with this camera down at the bottom left image of this picture.
So each of the little dots in that image is a single trapped ion of the isotope ytterbium-171.
Correct. Correct. And we have exquisite control over these individual ions that we use to store our qubits. And this is demonstrated by the fact that every single time we try to build up a chain like that, we do it by trapping individual ions way over here in this zone of the trap. This is the top view. And then moving them using electric fields by all of 1 millimeter along this path to put them in the middle. And we do it 1 ion at a time. And by doing this 1 ion at a time, as you can see here below, we build a necklace of ions by stringing ions, stringing individual atoms up like beads on a string. And you can see this here sped up about maybe 4 times. You can see the process viewed on our camera by which these ions are strung up. The pictures, as you heard, are produced by shining laser light that is resonant with the transition in these ions. And this laser light serves a number of purposes for us. It serves to cool these ions, to make them very, very cold, which we need for computation. It is used to initialize the quantum states and reset them, and also to detect which quantum states that in the end of the computation these are in. So it's used to perform measurements. Of note is that when you shine this light on ions, the ions scatter this light. And actually, even a single ion is quite bright. If you shine resonant laser light on a single ion, you can actually see it by eye through a microscope. Not ytterbium plus, because the color is the color of black lights. If you see black lights in clubs or in a fish market or something like that, this is roughly the color of our lasers. But barium plus is a beautiful cyan, beautiful aquamarine deep green. And if you look at it through a microscope, you can actually see by eye a single atom fluorescing. So they're, in some sense, they're relatively bright, each of them. They scatter a lot of light. Thanks to resonance, the beauty of resonance in physics, and we can see them and we can work with them this way. As I was saying before, the qubit that we use is stored in the internal states of ytterbium-171 ion, and these are the 2 hyperfine states, which are set by the relative orientation of the nuclear spin and the electron spin. So we have the electron, 171 ytterbium plus, one ytterbium plus in general, has 1 remaining valence electron. And so in the ground state, you basically have all paired electrons and you have 1 dangling electron in an S shell. And that electron now can interact with the nucleus via magnetic interactions. And the nucleus of ytterbium-171...
What's the nuclear spin of ytterbium-171?
It's 1/2. So
I see. So in other words, it's like a proton in that respect.
Exactly.
And so the states here consist of, if I'm just, I don't want to slow you down, but just for the benefit of the students, there's a proton and an electron, both of which have a spin of 1/2, and then they're aligned to form states of total angular momentum of spin 1. And I guess from your diagram there, Marko, it looks like the red state is when the electron proton spins are opposite, so they cancel out a net angular momentum of 0,
Yes.
and the blue has a net angular momentum of 1, as indicated by the first index in that cat, a notation that I've been telling the students is standard, and so you're seeing it here. And then the second index within the cat refers to the projection of the angular momentum along an axis. Is that correct?
That's exactly right. Yes. And in our case, that axis is set by the magnetic field that we apply, which is 3 Gauss.
So this is actually, in some sense, like the proton example, but sort of the horror of this week's homework exercise. Though, there the spin is a half, but still we have the same idea of a 2-level system with a quantization axis that's being chosen by, a committee of which Marko is a member. They come to a decision on how it's going to be aligned. And then once that decision is made, you have well, you can go on, Marko, a programmable qubit system.
Yes, and you can manipulate it, and the easiest way you can manipulate it is analogous to what you do in atomic clocks. You can just shine some microwaves at it, and these microwaves will couple these 2 qubit states. And so you can perform using microwaves, you can perform manipulations. Here's an example where a microwave pulse of variable duration is used to transfer the qubit from initially 0 state to flip it into the 1 state. And these microwaves, of course, need to be resonant, so they need to be around 12.6 gigahertz. What I'd like to, what was really cool kind of to notice is we bought these microwaves. You see how many digits we have. They need to be very stable, because this frequency is very stable. And this is why we like it as a qubit, because this frequency is highly, highly stable. That is because there's very little decoherence on this system. And the reason
so
is
the last digit in that expansion, the 8, that corresponds to 1 hertz, doesn't it? Or
yes, it does.
It's 10 to the minus 9 gigahertz.
Yes, it does.
So 1 hertz. In fact, you can't even hear a 1 hertz signal audibly. It's too low.
Yes.
Now, could I just ask about the data you're showing? What you do, I guess, is that let's take the 0.2 microsecond pulse length. What you've done there is to run the microwave pulse of 0.2 seconds, and then microseconds. And I suppose you then induce a transition from that upper state, the 1-0 state. And so this is how you detect. You induce a transition from the blue state there up to this, well, it's an ultraviolet transition, 369 nanometers,
yep.
And you see, and you get a fluorescent signal. And that's the source of that data.
Exactly. And we mostly get fluorescence if ion is in the upper states. If the ion is down here, then the laser that we're using to induce this fluorescence ends up being, actually turns out you have to add these 2 numbers, ends up being 14.6 gigahertz off resonant. And this 14.7 gigahertz is a lot wider than the natural line width of the inherent resonance of the 369 transition, which is 20 megahertz. And so you see very little fluorescence. If the ion is actually red, here's a histogram of the number of counts that we collect. And the blue is the histogram of the number of counts that we collect if the ion is in the upper state.
Yeah, beautiful. If you could go back to the previous figure, I'd just like to make another. So it seems to me that the way you do this experiment is you do just what you said at each recorded value of the pulse length here, and every one of those measurements is destructive because you've well, that's a question.
The
system does not return to its state. So in other words, you have to arrange the experimental protocol so that it can reliably produce this a well-defined in the single ion, the atom in the ground state spin down, and then do that over and over and over and over again. Maybe not even with the same ion, but I guess you can do it with the same ion.
We can do it with the same ion. In the case of one ion, actually the ion that I loaded at midnight last night is still sticking around. And I will show you that ion. The chains that we build up don't quite live as long. They live about half an hour for 15 ions, which is still pretty long.
And what determines that lifetime? Is it what are the mechanisms that cause an ion to disappear from the trap?
It all has to do with collisions of these ions with background gas atoms. The pressure that we have in our system is 10 to the minus 13 atmospheres. And at this pressure, okay, and you should think of these collisions as basically an ion is charged, and the atoms that are bouncing around, mostly hydrogen inside the vacuum chamber, are like little balloons, like little balls or balloons. Now, if you take a balloon and you put a balloon close to a charged stick, what happens? The balloon gets attracted to the charged stick. And the reason is that the electric field of the charged stick polarizes the balloon. It causes charge to separate inside of the balloon, such that if your stick is charged positive, the side of the balloon that's closer to the stick gets charged negative, and the side of the balloon that's farther from the stick gets charged positive. And that means that the negative charge in the balloon is closer to the stick than the positive charge. So you get a net attraction between your stick and the balloon, because the negative charge in the balloon is closer to the stick. And so the balloon gets sucked onto the stick. Same way, if a neutral gas atom, a hydrogen molecule, gets close enough to our ion, the ion will suck it in and collide with it.
Yeah, it'll make a hydrogen bonded ytterbium hydride cation, won't it? Or could do that.
It could do that, but in order to do that, it needs to get rid of excess energy. So that excess energy, that the binding energy of ytterbium hydride needs to go somewhere. And the only place it can go is into a photon. Right? Because the only way for the system to get rid of its energy, because there's only two bodies that are, well, I guess I'm a bit corrected. In a collision with a hydrogen molecule, you could potentially have ytterbium.
There could be a three-body. Yeah.
And H. Sorry.
Yeah, there could be a three-body. I guess.
Yeah.
Wouldn't it be the case that what you're mostly seeing is in fact hydrogen molecules?
In fact, we know that. Yeah, so experimentally.
You have a mass 2 signal in the, you're presumably using a residual gas, or, you do a residual gas analysis of your vacuum system, and I would guess the mass 2 peak corresponding to H2 plus would, and I think this is because it's hard to get all the water out of a vacuum chamber when it's been exposed to air. You bake it and you pump it, but I think isn't the water that is the last to leave?
Yeah, I can. Our dominant background is hydrogen, and we can actually use something very light, few AME. We can use the ion to actually tell us that. What we can do is we can use their trap to make a double well potential, such that the barrier height is such that it can be varied. So if you tune the barrier height to be higher than the energy you expect to transfer in a collision with a hydrogen molecule, if you indeed have mostly hydrogen, then you should see that your collision, you should see the ion stop hopping between the two wells. So if you have a double well potential for your ion and it collides with something, it will jump randomly between the two wells. And you can look at this rate of jumping between the two wells to see how often it's colliding. And for us, for one ion, it's about 20 to 25 minutes in a well that is whose barrier height is comparable to energy that you calculate in an average in collision with hydrogen 2, with the hydrogen molecule. And then if you make this barrier, higher by a factor of 2 or so, the rate of this hopping drops very sharply. So we can know based on this, based on our ion actually, our ion is a mass spec itself, to tell us that we have mostly H2. The other thing we know based on this is it's jumping between the two wells every 20-25 minutes. So it's colliding every 20-25 minutes. But as I said, I left it since midnight and it's still sticking around. So we know from that most of these collisions are not forming a molecule, because a molecule would not fluoresce. If we shine this 369 light at it, it would not be resonant with the molecule, and it is resonant still with our ion. So we know that we don't form the hydride very often. We do have there are some other. Yeah, so for single ions, these chemical react of ytterbium plus, these chemical reactions are not a big problem. I will note in passing that for some other ions like calcium hydride formation is a significant problem. So calcium, for whatever reasons of detailed molecular potentials, does tend to form calcium hydride, and you do get these dark ions that you can do mode spectroscopy of the motional modes in the ion trap, which I'll get to. This is how we do gates and 2 qubit gates, and you can tell that you have a calcium hydride based on that. But we basically do not see this. We may have seen this literally several times in 2 years of running. The more frequent event is that we get ytterbium plus. We get a doubly ionized ytterbium. And the reason that happens is the way that we actually manipulate, in an actual experiment, we manipulate the qubit. The microwaves that I was talking about previously, while they are easy to produce with a radio frequency source, you cannot address them onto a particular qubit, unlike a laser beam. So wouldn't it be nice if you had a addressable microwave beam? If you could say, I want this ion, but not the other one that's 5 microns away. I want to address this ion with microwaves, but not its neighbor. And in fact, this is what we have. We have a laser that, for most all intents and purposes, serves like an addressable microwave source. So it's a pulsed 355 nanometer laser. And this laser, its wavelength is its frequency is such that it fits kind of at this somewhat magic frequency in between these two excited states.
Oh, is that where the let's see, what do you call it? The electric dipole polarizability vanishes, or something like that?
Yeah, exactly.
It's exactly. a so-called magic wavelength.
Yes, it is.
So in other words, so the contribution to, like, so there's a possibility of off resonance absorption by an atomic line, and so this is a case where the amplitude for the doublet P1/2 state absorbing interferes destructively with that of the doublet P3/2. Is that a somewhat crude way of describing why you tune it there?
I would say no, not quite. It's the main reason is it's a convenient wavelength. 355 is available with lots of power, especially pulsed, because it's the third harmonic of 1064. Now, it is a fortunate coincidence, somewhat fortunate, that the net dipole force for this detuning is about 0. And that indeed, as Charles was saying, can be understood that if you think of the ion being in one state, like this state, then it interacts off-resonantly simultaneously with this state and with that state. And these two processes, where the ion off-resonantly absorbs this photon and then re-emits it, and where it absorbs via this state, and where it absorbs the photon into this state and then re-emits it, these two processes cancel. Which means that if the ion stays in one state, the net potential that it feels, the net energy shift that it gets from this is quite low. But if you include the hyperfine interaction with the nucleus, then you find that while this process is low, where the ion absorbs and comes back, the process where it absorbs and goes into the other state, the spin-flipped state, is actually maximal. So the coupling couples maximally to spin flips. So you can still scatter, provided you also spin flip.
I'd like to comment for the, let's say, Ben, are you an electrical engineering student? This is like so awesome, a demonstration of, how should I say it? Well, the 355 nanometer corresponds to a frequency that I guess is, 10 to the 14th, maybe even 10 to the 15th hertz. And you're using that, you're using that high frequency to control a transition that's at 12 gigahertz, which is like 10 to the 10th hertz. There's a factor of 10,000 difference between the wavelength that you are using to cause the transition and the between that frequency and this, it's a microwave oven frequency that corresponds to the energy difference between these two states from the equation E equal H nu.
Exactly. And that means that a lot of the noise processes in the laser that are associated with this 10 to the 15 hertz laser carrier frequency drop out. We are not sensitive to the direct phase noise of the beam coming out of the laser. We're not sensitive to the exact frequency of the laser. If the frequency changes by a gigahertz of the laser, we don't care. We're detuned from these states by tens of terahertz. So this laser, the only thing from the laser that the ion sees, if you go through the math for this process, is its intensity. It does not see the electric field of the laser itself directly. It sees only the intensity profile in time of the laser. I will note it does see the electric field of the beams that are incident onto the.
Right.
There are two beams that are incident, but the effect of the phase noise of the laser, rather than these two individual beams, cancels.
So in that equation at the bottom,
yes.
Raman Hamiltonian, it's proportional to the Pauli X matrix. Is that correct?
That's exactly
so
right.
This is the X gate of a qubit that basically it's it's 0 on the diagonals and 1 on the off diagonals, and that you can see that is something that causes a spin down state to be flipped spin up, and vice versa in a very symmetric fashion.
Yes.
So here's someone actually making an X gate with a laser.
So we use an open source control system, spearheaded by, initially initiated by the people at NIST Boulder, the ion trapping group there, in order to control our system. And it's called Arctic with a Q, and it provides real-time control of various devices. By real-time, I mean that when you tell it to do something, to turn on a laser beam or turn off a laser beam at a particular time, it does it at a deterministic time with a resolution of about a microsecond. And
I think this system is in widespread use in the ion trapping community, isn't it?
Correct, correct. And we use Arctic as the, if you will, the glue that controls kind of everything, everything in the system. And what I'm showing here, I just started one of these real-time Arctic experiments. And what it's doing is we have photomultipliers that detect the light that comes from each of the ions. So you're actually watching this fluorescence from one of our ions. I think from one ion, yeah, from one ion, the one from last midnight, because I did not reload it. And it's counting 24,000 counts per second. The y-axis is in kilohertz. You can see it.
And this is light that is scattering out of a probe beam, or what exactly?
Exactly. It's light that is scattering from a probe beam. There is a resonant laser beam that is shined on the ion, and it's currently also doing double duty to perform laser cooling of this ion.
Okay, so is this at the 355
369
nanometer way?
369. Yes. And so now I'll stop this. We see that we have an ion. It's reasonably happy. I'm gonna do a quick centering experiment, just to make sure that my 355 is aligned, and I can explain what this does. So what I am doing now is I am applying a, let me see that there is a signal before I talk too much. Yeah, good. So I'm using the voltages in the trap to move the ion along the axis of the trap. And for each of the positions of the ion, shown here on the x-axis of this applet, I do a 0.6 microsecond duration pulse with the 355 nanometer laser beams. And this causes the spin to flip partways if it sees the light. And after that, I shine this resonant light to ask, is it in the 0 state or is it in the 1 state? I do this 250 times, and then I show the mean. And I use that to determine where the center of my beam is. So once I've now centered to the middle of the beam, I can simply apply a variable duration pulse, just as with microwaves. And I can see the ion go down, up, down, up, down, up. I think it should be there. So the ion starts in 0, as with the microwave pulse. And then as I vary the duration of the laser pulse that I'm applying here in microseconds, the population switches between the lower state and the upper state. And again, each of these points is an average now of 200 shots. So there's 200 experiments whose average is shown as each of these points. That's that makes sense.
So we're seeing the oscillation from one state to another It's just a perfect induced by an external field.
Yeah.
It's a classic experiment. Basis of atomic clocks work in the same way, don't they?
Yes.
Well, with differences, but I mean, this system, the system that you have, could be used as an atomic clock for exactly this reason. I mean,
yes.
there'd be a different control and readout protocols, but the physics package, if we call it that, the single trapped ion would be a actually, yeah, I think the reason that you're using a control system that was developed in Boulder, Colorado, fundamentally is because that's where the trapped ion effort, the trapped ion research for use in atomic clocks was developed.
Yes.
For better time and frequency standards.
Yeah. Yeah. And I want to show you, if I go to about half a microsecond, so to this point, and just do the repeated experiment. So I'm going to do 50 shots for 1 point, average of 50 shots in 1 point, and I'll keep repeating this. So I won't vary the time. It will show that you're varying the time, but I'm not varying the time. I'm just doing the same experiment over and over again. And I'm looking at the average. And you see the average is scattering up and down because there's shot noise. Sometimes the ion's down, sometimes the ion's up. Every time I do an experiment, I either get up or down. And if I do here 50 shots, I should get about noise of 1/8, which is roughly what I see here. That I have a noise of about 1/8. I think that's clear. If I've explained that, I want to use this to show something else.
Could you explain again exactly what you're doing here? Is this like, are you taking a projective measurement of some sort that has a nominal probability of 1/2, and then seeing? Okay, so this is like, I'll say, we could discuss this in saying, well, we have a horizontal, an optical polarizer with a horizontal pass axis, and we're sending it into it a stream of photons that are polarized along the diagonal direction, the D direction of H and V. And so there's a 50% probability of detecting a photon. And you see that emerge in this scattered shot that you have. Well, I mean, maybe the average is 0.49 or something. I don't know. I guess you can tell that from analyzing the data. But we've got this nominal probability of 50%. But what we actually see is a fluctuating signal because it comes from, an individual single quantum process. Is that a reasonable interpretation?
Yeah, exactly as you said. Yeah, exactly. And what I'm doing now is
so all this studying of polarization that we did in the class. Would you say it was a total waste of time, Marko?
No, not at all.
There you have it.
Not at all. Not at all. And I mean, it's interesting when you work with these quantum systems, especially ions, where each experiment, each of these, each shot, each point here is 50 experiments. Each experiment takes a few milliseconds because you need some time to do the schooling of ions and preparation of ions and so on. So you need to, so you already notice you need to wait to accumulate the statistics. If you want to know what your probability is between 0 and 1, you actually need to wait and do enough experiments to sit around, watch YouTube, get a cup of coffee until the ion has told you what the probability is. So this averaging is very much felt with ions. You feel you're literally sitting in your chair for so long in order to determine what is my state. And so here, I'm showing the fluorescence signals from now an array of 15 PMTs. So each ion is, for us, is coupled into a fiber, which goes to one photomultiplier tube. So each of these photomultipliers acts to detect the states of one ion. And what we're doing is we're assembling this necklace, one ion at a time, and each of these blinks that you see is an attempt, and now it claims it has loaded 15 ions, or nominal configuration here. And
so each color on that plot corresponds to a different photomultiplier.
Correct, correct.
And each photomultiplier is imaging one of those, whatever it is, 30 ion sites that you were showing us.
Exactly. Exactly.
It's monitoring a particular ion in the linear array of ions.
Yes. And it claims it's loaded 15 ions. Let's see if it has. The way we check is we take our chain and we slide it through our beams. So we move now the whole chain along the axis of the trap, while using all of our beams to apply the same pulse of half a microsecond. And when the chain is centered right there, when the chain is centered on the beams that are used to manipulate the ions, you see all the ions, most of them except these two, are transferred halfway. And then if you're off to one side or to the other, you see less transfer. These two are edge ions, which are a little bit misaligned because there's nothing to hold them. They kind of like spring out. Coulomb repulsion kicks them a little bit, misaligns them a little bit.
To be clear, you're doing this in real time.
I'm doing this in real time. Yeah, as
so
I'm talking.
We're not reviewing data that was taken long ago. It's produced on demand.
It's absolutely live. And so now I want to show, having loaded 15 ions, now I have 15 qubits, right? I've loaded 15 ions and I can control them, as you can see on this plot. I have 15 qubits. So, so now what we can do is, we were discussing single qubit operations so far, right? And what I can do now is, instead of doing a sigma x operation, let's try doing a sigma x1, sigma x2. Do x operations on 2 qubits together. So now the 2 qubits will be simultaneously flipped. Give me 1 second. So I'm going to do the same experiment.
Oh my God! So you can pick out individual ions.
Yep. I can pick out individual ions, and I can apply laser beams to both of them, a pair of ions. And
so it's ions 2 and 3 from my reading.
Ions 2 and 3, exactly, as I typed in here. And I am going to apply sigma x on ion 2 simultaneous with sigma x on ion 3, coherently. So the operation is sigma x, sigma x.
Whoa. And
this should work well enough. And again, 64 shots per point. I'm going to do 11 points. Let's do a little bit, few more, 16 points. And
you're applying a pi pulse, is that correct?
I'm applying a pi quarter XX gate. I'm applying XX. The goal is literally the unitary that I'm aiming for is XX.
Right. Okay, good.
And here we go. What did they say for live demos? Ah, excellent. There we go. And you can again see shot noise, right?
But only ions 2 and 3 are being transferred. The rest of them are just not. Sort of, yeah, there are little fluctuations or so. But I guess there's some fluctuations in the signal to the photomultiplier that aren't associated with important things going on in the ion, just statistics of the emitted photons.
On the target ions, exactly. We are again seeing this well, we're seeing the statistics of zeros and ones. This is only 64 shots, so I expect to see 1/8 scatter up down by binomial distribution, just as you did with one ion. But look at this curve. The two ions are correlated. They are scattered, but they're scattered simultaneously.
Wow.
The shot noise is now very correlated between the two ions. And the reason is that the state of the system for 1 qubit was 0 plus 1 over root 2. The state of the system now is 0, 0 plus 1, 1 over root 2.
Yes, I guess that is a vivid demonstration. So you have, yeah, I guess, and by the way you're applying the pulse, you do get coherent. I mean, just if you take the since they're both in the same quantum state and they're being driven with a common external input, they will well, no, you say they're entangled. Is that what you were saying?
I am saying it's plausible that they're entangled. They're correlated. They're certainly classical.
They're correlated. Yeah, they're correlated.
Now, oh, somebody kicked me off. So now I need to Slack people. Please don't steal the machine. I was supposed to post on Slack that the machine is being used. Yeah, we have a grad student who wants to run lots of gates now.
Well, maybe, I mean, this is fantastic. I mean, it's just, you know, vivid illustration of what's possible now. And you know, I could watch this sort of thing go on forever, but I understand you have an interview coming up or something like that for a postdoc.
We have a postdoc presentation exactly happening, but I do want to finish by dispelling doubts about, if you allow me to say that, about whether we have entanglement. Here's a parity fringe for the same state with the analysis pi over 2 pulse. So now I'm saying I have entanglement. Very good, pretty good entanglement, in fact, about 95% probably fidelity. The error is probably, you saw that they were not 50-50 between 0, 0, 0 and 1, 1. That's probably the error. It needs a little bit of intensity calibration. The typical fidelities are 98 to 99 for XZ gates, for a single XZ gate. So.
Okay, well, thank you so much for taking the time. I mean,
sure.
It's always inspirational to see these experiments, and I mean the things that are done here. Well, I think Chris Monroe started using ytterbium-171 maybe 15 years ago, more than a decade ago. And to see the, I think I looked up a paper I think it was dated 2008 with Steve Olmshenk as
yes.
an author. Yes. Early work, I guess, actually done maybe partly at Michigan and partly at Maryland. I forget. In any event, the progress in this ion trapping field is just phenomenal.
And I want to point out that usually we don't run our experiments with that interface. We go to a Jupyter notebook and we write circuits. So each of these is so like literally this one here is the gate I was just doing. The Smolmer-Sorensen gate, XX gates between these two ions. This is the one I was just showing, and I was showing these RYs for the parity fringe and RZ. But this circuit is making a 5-qubit GHZ state, and just 12 hours ago, oh, this was showing just the populations. The parity was 0.9 amplitude for this circuit for 5-qubit. So this circuit is making 0, 0, 0, 0, 5 zeros plus 5 ones on 5 qubits. And you just program it very much like IBM quantum experience or IonQ systems. And yeah, and you do this with this 98, 99% fidelity for the gates, for the entangling gates. Yeah, and you can set it to run and come back in a few hours and tells you it's finished. If it loses ions due to collisions and so on, it will automatically reload them, recenter the beams. So everything I was doing now is automated by now. And you can just let it run. And that's what I was getting the ping about. Other people want to use it.
Yeah. Marko, would you have any objection to my making this recording publicly accessible? I mean, you've explained things so well, and they bear on these fundamental issues. I think it's possible they would, well, or maybe just think about it. I think it'd be great to have a sort of a tutorial material based on this type of presentation.
That is fine, actually. I was I know what I've presented. There is nothing unpublished touchy about it. Yeah, you can absolutely post it.
Well, thank you so much. And now we're going to go off and talk about some of our own little homework problems. But I really appreciate the time you've taken.
You're welcome.
To me, it's inspirational.
Pleasure.
Thanks so much.
Okay, bye, everybody.
Bye-bye.
Thank you.